Hello everyone. So we have discussed about the experimental techniques of producing dynamic deformation in earlier lectures. So in today's lectures we will discuss about the plastic deformation at high strain rates. So you will see some constitutive relations, that is a relation between stress and strain or other quantities like strain rate or temperature, and we will get these equations, the mathematical relationships, and also we will see how the defect structures, the crystal defects influence these relations. So plastic deformation at high strain rate. So plastic deformation at high strain rate. So I will write high strain rate as HSR, so that will be easier for me. So plastic deformation at high strain rate have a relation between stress and other parameters like strain rate and temperature. So as we know that in the elastic region we have only Hooke's law, that is sigma equal to E epsilon, but here if you are talking about the plastic deformation at high strain rate, we need to consider the strain rate epsilon dot, and we can also consider temperature here. So this is the constitutive equation. I am sure you know what is constitutive equations. You probably studied in your solid mechanics classes. Constitutive equations for high strain rate plastic deformation. So as we know, this plastic deformation is irreversible. It is irreversible, and hence it is also path dependent. It is also path dependent. So that's why the deformation substructures here in this book, that using the phrase deformation substructures, which means mostly the defect structures like dislocation structures in the material. So this deformation structures influence the material behavior or the plastic deformation behavior. So what we need to do is, because this deformation substructures influence plastic deformation, so we can rewrite the earlier expression like epsilon dot comma T comma deformation history. Deformation history. So why we are writing deformation history? So this will denote the evolution of deformation substructures So that means suppose in most cases the dislocations, how the dislocations evolves means with time, with deformation, how the changes happens in dislocation structure or the deformation substructure, and these deformation substructures also depends on the evolution, depends on strain rate and temperature. So that depends on that. These so some plastic deformation theories, some plastic deformation theories use some effective stress and strain to express these plastic deformation, like sigma effective is equal to root 2 by 2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square to the power half square root of the whole thing, or maybe effective strain, which will look like this, epsilon 1 epsilon 2 square plus epsilon 2 minus epsilon 3 square plus 1 minus epsilon 3 square half. So these are these effective stress and strain. They are taken as a scalar quantity, although these are tensors. So we are not going to use this. So there are some other options like shear stress, and that is tau, and shear strain, that is gamma, can be used to express these plastic deformation theories. So because metals and also polymers, they undergo plastic deformation by shear, plastic deformation by shear. So that's why we can use shear stress and shear strain to plastic deformation and then to come up with some theories. So also more advanced and advanced analytical treatment and computational schemes, they use tensorial approach, which we are not probably we are not using that tensorial approach, because it will be a little difficult for us, because you have different backgrounds, so you probably did not study about the tensorial approaches earlier. So that is, we are talking about the advanced theories, or analytical treatment and computational methods. So I will just write analytical treatment. So these theories probably will require tensorial approach with fully calculations with tensors. So if we plot the yield stress with shear strain rate, so that is we call we can call, let's say, gamma dot. So this plot, whatever we will be showing, is from Campbell and Ferguson. So the yield stress, as it is for mild steel, so here they are using the lower yield stress. As you know, there will be the yield point phenomena. So the stress strain curve will look like this. So this is the lower yield stress, LYS. The upper yield stress is this one. So this is the stress strain diagram we are seeing, but here what we are showing is the yield stress. So how it look like is, suppose we can see that the yield stress will increase with strain rate, and So what is happening here is this is in logarithmic scale, log scale. So let's say you have 1 here, 10, 100, 1000 like this, 10,000. So here let's say 0.1, 0.01, something like that. So here we are not plotting whatever megapascal values here, but this is the first curve is for very high temperatures, 713 Kelvin, and then second one is 493 Kelvin. Probably these are very this will be close to each other, and then the third one let's say 225 Kelvin, and the last one is 195 Kelvin. So just to show you the variation here, so there are two observations they made, that is yield strength increases with the strain rate, and the number 2 is that increase of yield strength, is very prominent or significant at lower temperatures. Lower means as compared to these 713 or 493 Kelvin, these are lower. So the increase, the difference is higher in that lower temperature range. So what we will discuss next is the constitutive model. Constitutive model for high strain rate plastic deformation behavior. So what we need to do is, so whatever we have seen in this plot, so that can be the summarized. If you can summarize the data, data means that from that plot into a equation, the mathematical equation, if we can plot into a single equation, that means that should include that strain rate variation and temperature, these effects. So we will try to find, and then what we can do is then we can interpolate or extrapolate to predict the material behavior at different strain rate or at different strains or temperatures. So that's what we will do, that to find a constitutive model for a suitable or appropriate constitutive model for high strain rate. There are several equations were proposed, and even equations means constitutive equations, they were proposed and even successfully have been used. So the objective of this equation is to summarize the yield stress behavior, the variation of the yield stress with strain rate and temperature. So suppose if we try to have this relationship between stress and strain in the plastic region, and that there is a relation which is a good approximation. So this is at low strain rate, low and constant strain rate. So and then if you want to talk about the flow stress dependent on temperature, so there is another model that is put forward is like this 1 minus T minus TR, Tm minus Tr. So we will see what these means. Similarly, if we want to see the variation of flow stress with strain rate or effect of strain rate, So that stress is proportional to natural logarithm of the strain rate. So here in the first equation, this sigma naught is the yield strength, and n is called as work hardening coefficients, and k is a pre-exponential factor. That I think all of you know that this is work hardening or strain hardening exponent, or we can call coefficient, and then k is also a constant. This is we generally write as pre-exponential factor. So similarly, for the flow stress temperature dependent relation, that is sigma r is the reference stress, Tm here is the melting point, melting temperature, Tr is the reference temperature. So m is a experimentally determined. This is the fitting parameter that you know when you want to fit your experimental curve. So with this equation, so we may need this fitting parameter, and then the third relation is the sigma that is directly proportional to natural logarithm of epsilon dot, that is the strain rate. So that is also not very high strain rate. It's not very high. Probably this relation, it's not for very high strain rate, but we can go to moderate high strain rate. So if we want to plot these variations, so we can get like this yield strength, and the temperature curve will look something like this. So that with temperature increase, so yield strength will decrease, and the curve looks like this. And again, if we draw the yield strength variation with strain rate epsilon dot, so this will vary like this, and if you are talking about a lower temperature, so it will look like this. So this is T1 and T2, here T2 is higher than T1. So these are the plots, the shape of the plot. Sorry, this line doesn't look very good. So these are the shape of the plots. We'll talk about now Johnson-Cook model of plasticity. So which is very widely used and successful for, especially for high strain rate. I will write HSR, high strain rate, for high strain rate plastic deformation behavior. Johnson and Cook basically summarize and then use the basic ingredients like the stress dependence on strain, temperature and strain rate. So using these basic ingredients and proposed a relationship which is equal to sigma naught plus b epsilon to the power n 1 plus c natural logarithm of epsilon dot divided by epsilon naught dot, and then 1 minus T star to the power m. so the power for the T star only. So this equation have 5 experimentally determined parameters. So here you got sigma naught, B and N, here you got C, and here you got M. So these are the 5 experimentally determined parameters. So this equation, this model, it's was very successful, and has been predicted the plastic response, plastic deformation of many, especially metallic materials. This is for metallic materials, many metals at high strain rate or under high strain rate loading. So this predictions was actually predictions are very successful for many metallic materials, and these parameters are already available. So you can see in the let us say table 13.1 in the Mark Mayer's book. So you can see all these parameters in a tabular form, and then for many materials these are already available. Suppose for N is whatever you can see from this table, is the range is 0.1 to 0.42. Generally this varies from 0.1 to 0.6, but whatever I am showing, I mean I am focusing is that only this table, and this table has, I will just speak, I will not write all those. So OF, HC copper, Curtis brass, nickel 200, Armco iron, and then Carpenter electrical iron, 1006 steel, 2024 aluminum, 7039 aluminum, and 4340 steel, and there are 3 more materials. So these materials have a you can see the range of N is like that, and then C will be it's a smaller value, 0.007 to 0.06, and then M which is the thermal actually exponential thermal softening exponent, which is mostly it is equal to 1.0 or even higher or higher. Even there are some lower values are also available. So and sigma naught and B are which are we express in terms of megapascal. So they are also kind of it can vary from 100 to 1000. These range are, let us say 100 or even less than 100 to 1000 in this range, these parameters, but these are experimentally determined, and so for many materials these are already available, and we did not discuss about this T star. So T star is equal to T minus Tr, which is the reference temperature, and then Tm melting temperature minus Tr. So this we already got this in the earlier slide. So this is we already wrote. Epsilon dot in this equation, epsilon dot not is a reference strain rate. It's taken generally as 1. For convenience, this is actually reference strain rate, and then sigma naught is the sigma naught is measured at reference temperature Tr. So Tr the reference temperature, sigma naught is measured at that temperature. Also, as I told, this is used for mostly for metals, but sometimes it is also modified for ceramics as well. This Johnson Cook model has been modified for many materials. This is some of the researchers, they modified the equation a little bit, and so that it can fit to different kind of materials. And so some researchers even they tried it for ceramics, and they were able to get reasonable prediction from this Johnson-Cook model for ceramic as well. As you can see that there are different models. So these models will have exceptions. So it is difficult to propose one theory, propose a unified theory for all materials. So that is not possible, because so materials are all different, they follow different rules, so it's not possible to get a unified theory. And also this is the first point, and the second point is there are different deformation mechanisms. So different deformation mechanisms, that means plastic deformation mechanism, that we already discussed in our materials basic lecture. So as we know, we have dislocation slip, twinning, and phase transformations, or mostly we discussed about martensitic transformation. So here in this section we will only talk about slip, that is dislocation slip, not the other two. So here we will talk about this one edge dislocations. Here we have edge dislocation. I hope this figure is clear to you. So this is an extra half plane. So this extra half plane, these lines, vertical lines or an horizontal lines, so the atomic arrangements, we are not drawing the atoms, but showing only the lines. So these whatever I am highlighting with red color, so that is the extra half plane. And if you say where is the dislocation line, that is perpendicular to the plane of this diagram. So and then this is the slip plane. The slip plane is we were seeing in 2 dimensional, but if you extend it to the 3rd dimension, you will get the slip plane. So now this dislocation is moving towards right, and then it is now after this, first it was let us say we are talking about a perfect crystal. Here we have a dislocation, and then if the dislocation moves, so there is one step created that is equal to Burgers vector B, the magnitude of this. And here also maybe this is same as the Burgers vector B, one step, one atomic distance. What here we are doing is we are applying some shear stresses tau, which is in this direction also you can show. This is we are applying some shear stresses. So shear stress tau moves the dislocation, Here in this case we are showing only one edge dislocation. And here again in the lower figure, what we will see is that, let us say we have a square domain of material, that is it's a L and L length, and then let us say we are applying some shear stress tau, and there are some dislocations. The dislocations are can be shown with this symbol, that is the symbol for dislocation. So we are drawing, let us say 4 dislocations here. So these dislocations, when they will move this direction, they can have, so this is one slip plane, let us say number 1 dislocation move and can create a step here. Similarly the other dislocation, a parallel slip plane will move and create a step means the making a step here. Similarly another dislocation can move and make a step here, and then another parallel plane here. So finally the shape will be look like this. So this final shape will be look like this. So So this angle, let's say assume this angle is theta, and so now what we will do is, so this second figure, that means in the lower figures, the above top two figures, so below two figures, so what it says is that movement of array of this location, movement of array of dislocations results in shear strain, gamma. So array means, as you can see, we have drawn 4 dislocations here, and also on the same slip length, just I want to clarify this, on the same slip system there will be more dislocations. So so after one dislocation, here for our simplicity we are showing that just one dislocation is going out of the crystal, but there can be more dislocation on the same slip system, there can be hundreds or thousand of them. So so movement to the area of dislocation will result in a shear strain, that is gamma. So we will see how to calculate this gamma. So this shear stress, the force on the dislocation per unit length in this case is force on dislocation. So we will write per unit length because the dislocation is a line defect, so it looks like a line. I have not shown you any figure, but if you see in transmission electron microscope TEM, the dislocation will be seen in that transmission electron microscope, and this dislocation will look like like noodles, like Maggi noodles. So so these are lines basically, though that may not be a straight line what we are seeing. Some of our diagrams, even in materials basics lectures, we saw a straight line as a dislocation, but that may not be the case. That can be that can be a curve. So and that may look like some noodles. So what happen is, so when you are calculating the force on the dislocation, so you need to calculate the force per unit length, not the entire length of the dislocation. Entire length can be very high. We even don't know, and it is difficult to discretize and say that okay, this is one dislocation or something like that. It may be continuous curved line. So that force will be equal to tau, that is the shear stress, multiplied by the magnitude of the Burgers vector. So Burgers vector, so that means that is the dislocation Burgers vector you can write, or that offset that caused by the dislocation. Here you can see this is the Burgers vector magnitude. So if one dislocation goes out of this surface, that is the distance is b. So this is the force per unit length acting on the dislocation. Now we will see another thing, that the gamma, I will write it here only, although it does not look good, but this gamma, that shear strain will be equal to tan theta in this case. From your definition of shear strain, we know that, let us say this portion is L, and we need to know this distance. So how to get this distance is, we know we are assuming this one step is B, or in this side also you can see that this is B, or even this portion is also, let us say, B, and again this portion is B. So here we are not assuming that, let us say, array of dislocation, but let us say we are talking about only one dislocation now. So then only one step, and this step length is, we can say that equal to B. So now if you have 4 dislocations, we have here also B. So if you have 4 dislocations, so then it will be, the total distance will be 4B. Now instead of writing 4B, we can write NB. So N is number of dislocations per unit area. So you can get that gamma equal to tan theta, which will be equal to now NB by L. You can see this is, if you see this triangle and this angle is theta, triangle means I want to tell you about this triangle, and this is the perpendicular and the base, so NB by L will be equal to gamma. Okay, so we will write again here. So gamma will be tan theta, which will be equal to NB. N is the number of dislocations per unit area, B is the magnitude of the dislocations, Burgers vector, and then divided by L. L is the our domain or size of the materials sample, and then what we can do is we can write it like this, NBL divided by L square. So we are multiplying L both above and below, and so we should know that the number of dislocations per unit area and divided by L square will give us the dislocation density rho. That is the dislocation density. So this is dislocation density. So here what we can do is we can write now N by L as rho NBL. So that is equal to gamma, that's shear strain. So here I will write shear strain. Shear strain produced by the dislocation movement. So now we can take the time derivative. If we take the time derivative, then we get that d gamma by dt rho b derivative of L with respect to t. So d gamma by dt is nothing but the shear strain rate with a dot on top of it, and then rho b, and we can write v, small v. So v is the equal to dl by dt. So this dl is, you can see we have L here, this L. So the dislocation moves at, let us say in time t, if it if it moves in the x direction, and then if we take the derivative of L with respect to t, that will give us the velocity of dislocation. Velocity of dislocation. So so this equation is very important, and this is called as Orwan equation. So that equation shows the relation between shear strain rate. So here if you want to know, this gamma dot is shear strain rate, rho is the dislocation density, we have already written there, dislocation density, and b is the Burgers vector, magnitude of Burgers vector, actually Burgers vector magnitude, and v is the, as you know, velocity of this location we have wrote here. The shear strain can be converted to longitudinal strain epsilon by adding a orientation factor, So here in this book it is not discussed in details, but other books probably from the mechanical behavior of materials, Mayers and Chawla, so they are referring it to it. And then this this is orientation factor, that is M. So M is can be different for different crystal structures. So from this book from Mayers and Chawla, so they are saying that M, they are taking M 3.1 for FCC material and M equal to 2.75 for BCC, body centered cubic metal. So what the expression I did not write yet. So d epsilon by dt, that is epsilon dot will be equal to 1 by rho bv. So the M factor is different for different materials. In a generalized tensorial form, just I want to write that, but we are not going to discuss at all. This will be little advanced for you. Generalized tensorial formulation is it is so plastic strain rate is K equal to 1 by N B. I'll let you know what is K, and then rho V K. So you know what is B rho V, and then M K and this N K. So so these are the vectors. I will tell you what is this. And so basically what happens here is this K 1 to N is the number of slip systems. So these are the slip systems. So as you know, there are different number of slip systems. So in FCC materials this N can be 12. So for each slip systems the contribution should be calculated, and here M and N. So this is we are writing the product of tensor product of M. M is for each slip systems this slip direction, as I told in the earlier class of materials basic. This is the slip direction, and N is the slip plane normal direction. These are the vector slip plane normal direction. So so just to let you know that the slip direction and the slip plane normal direction can influence this. So that's why, although whatever we got earlier is a simple expression, but then this slip systems can influence this the strain rate here, the strain rate in the longitudinal strain rate. So this is we don't need to discuss more on it, but this is an important result. So with that, so we are actually closing for this lecture. So what we discussed here is we discussed about the constitutive relations, empirical constitutive relations, which is a very successful one equation is Johnson-Cook model, and we also discussed about the basic high standard plastic deformation and relations between stress, function of strain rate and temperature, and that relation can be is summarized in with the help of this Johnson-Cook model, which is the most widely used, but there are other models also available in it. And then we also found about this Orwan equation. The Orwan equation gives the relationship between shear strain rate with the density of dislocation and this the velocity of dislocation. So we will continue this discussion. So we have more to discuss about the plastic deformation behavior at high strain rate. So thank you.